Настиг меня догнал, он настиг меня догнал, он настиг меня догнал, ты меня догнал, ты меня догнал, ты.
There are several complexity classes, but let's focus on two, P and NP. P stands for polynomial time and refers to problems that can be solved in polynomial time, or ONK, for some constant k. These are considered efficient algorithms because the time it takes to solve them increases at a reasonable rate as the size of the input increases. On the other hand, NP stands for non-deterministic polynomial time and refers to problems that can be verified in polynomial time but not necessarily solved in polynomial time. These problems are considered to be intractable because the time it takes to solve them increases exponentially as the size of the input increases. Now, there's an important question in computer science. Is P equal to NP? In other words, are all problems that can be verified in polynomial time also solvable in polynomial time? It's one of the biggest unsolved problems in computer science and has important implications for cryptography, optimization problems, and more. To give you an idea of how important this question is, let me tell you a little story. In the 2006 movie The Da Vinci Code, the main character, Robert Langdon, is tasked with solving a code that will reveal a secret location. The code turns out to be an NP problem, and Langdon spends hours trying to solve it. If P equals NP, Langdon could have solved the problem much more quickly, and the whole movie would have been much shorter. Now, for you PhD students, I encourage you to explore complexity classes even further. There are many important classes, such as NP-complete and co-NP, that have implications for many areas of computer science. So keep learning, keep exploring, and who knows, maybe one of you will be the one to solve the P versus NP problem someday. At this advanced level, we will cover the finer details of algorithm design, analysis, and implementation. We will delve into data structures such as trees, graphs, and hash tables, and explore how they can be used to optimize the performance of algorithms. To begin with, let us define what an algorithm is at its core. An algorithm is a well-defined procedure that takes an input and produces an output. It is a set of steps or instructions that solve a problem or perform a task. In computer science, we often use algorithms to process large amounts of data and make decisions quickly and efficiently. In order to analyze the efficiency of algorithms, we use a variety of methods, including Big O notation. Big O notation is a mathematical tool that allows us to compare the relative efficiency of different algorithms by looking at how they scale with input size. Now let's move on to data structures. A data structure is a way of organizing and storing data so that it can be accessed and manipulated efficiently. Different data structures are suited to different kinds of applications, and the choice of data structure can have a big impact on the performance of an algorithm. For example, trees are a data structure that can be used to efficiently search for and retrieve data, while hash tables are useful for quickly looking up data by a unique key. Graphs are used to represent complex relationships between data points, such as social networks or roadmaps. In addition to understanding the theoretical underpinnings of algorithms and data structures, it is also important to be able to implement them effectively. This involves choosing the right data structures for the task at hand, as well as writing clean, efficient, and bug-free code. One real-world example of the use of algorithms and data structures can be found in the movie recommendation systems used by streaming services such as Netflix and Amazon Prime. These systems use complex algorithms and data structures to analyze user data and make personalized recommendations based on a user's viewing history, ratings, and other factors. In conclusion, the study of algorithms and data structures is a crucial part of computer science, with wide-ranging applications in fields such as artificial intelligence, machine learning, and data analysis. By understanding the theory behind these concepts and developing the skills to implement them effectively, we can build more efficient and powerful computing systems that can solve a wide variety of complex problems. In the previous segment of this lecture, we discussed the concept of computer networks, including the different types of networks, their components, and how they operate. Now, we will dive deeper into the protocols and technologies that make these networks possible. Firstly, let's talk about the Transmission Control Protocol, TCP, and the User Datagram Protocol, UDP. These are the two most commonly used protocols for transmitting data over the Internet. TCP is a connection-oriented protocol, which means that it establishes a reliable, ordered, and error-checked connection between two devices before data transmission begins.